Today's visualization is the Lorenz butterfly, one of the most famous pictures of chaos in mathematics. What you're seeing right now began as a simplified weather model. In the early 1960s, meteorologist Edward Lorenz tried to simulate convection in the atmosphere using just 3 differential equations. When he rounded his input numbers, he expected a similar forecast. Instead, the result was completely different. That tiny change produced a totally new path. The discovery that small causes can lead to huge effects. This became known as the butterfly effect. The system is defined by 3 coupled equations. dx dt equals sigma times y minus x. dy dt equals x times rho minus z minus y. dz dt equals xy minus beta z. The variables x, y, and z describe an idealized fluid flow. Sigma, rho, and beta are constants that control how violently it moves. In our render, we integrate these equations step by step, updating x, y, and z thousands of times per second. As the curve traces out, notice how it never settles into a simple loop and never flies off to infinity. Instead, it orbits around 2 invisible wings, switching unpredictably from one side to the other. This shape is called a strange attractor, a structure that pulls trajectories in, yet is infinitely detailed and never exactly repeats. When the view shifts to graphs versus time, each spike and oscillation is one coordinate of the same system, unfolding like a chaotic heartbeat. The phase plane views show how x and y chase each other in spirals, while the side view reveals the vertical motion hidden inside the swirl. In the final shot, everything comes together into the classic butterfly shape. 2 spiraling lobes woven from a single continuous path. A tiny nudge at the start would produce a completely different journey, but always within this same delicate outline. The Lorenz Attractor is a reminder that simple equations can generate astonishing complexity, and that behind apparent randomness, there can still be structure and pattern. This is the beauty of chaos. Subscribe for more CM2A explorations.